Thank you very much, and cheers. Best way to start a presentation. So welcome everyone. I'm happy to speak in front of all of you. As I said, my name is Andreas Wölfl, and I'm talking about container-based virtualization today. But before we get deep into the topic, I first want to introduce myself properly. So I'm a kid of the Bavarian forest. To be more precise, I was born in the pearl of the Bavarian forest, which is a town called Bodenmais. You should visit. There I grew up, and I landed in Passau in 2004, where I studied computer science in the University of Passau, from which I graduated 2011. Then I had basically two endeavors. The first one is I did a lot of freelancing and software engineering, mainly in the online marketing sector, where I helped my customers in their digital transformation. And then I did a PhD also at the University of Passau in cooperation with Airbus Helicopters. And in my PhD work, I was concerned with data management in avionics systems. So the electronic devices that you find on aircrafts and helicopters. And as was said before, since 2019, I'm very happy to be part of the OneLogic team. And I'm a DevOps engineer here. So, and this picture describes best what I do all day. So I'm concerned around questions how we can smoothly and quickly package our software solution and transport them to the operation environment at our customers. But it's not only OneLogic where container-based virtualization is used. This technique is widely adopted in modern industry, which is corroborated by the annual container adoption survey, which is done every year by a research marketing company called MarketCube. And this company asks 500 IT pros around container usage, tooling, environment, and adoption barriers. And these participants were not just any random guy from the internet. They were screened before, and they needed in-depth knowledge about the IT strategies in their companies. And the company must have at least 500 employees. And the result of one of the key questions you can see on the slide here on the right-hand side. And the question states, does your organization run container technologies? And as it turns out, 87% of the participants answered with yes. So it's widely adopted here. But what is more interesting is the question, does your organization run container technologies in production? Because it's a whole different thing to just play around with the technology and try it out somewhere, or to add this technology as part of your solution that you carry out to customers. And roughly 90% of the 78% say, well, yes, we use container-based virtualization in production. So it's not just any hype that's over in a year or two. Container-based virtualization is really a technology that is widely established in businesses around the globe. So it's worth to take a look at the core principles of container-based virtualization. And the principle goes back to the 1950s. To a scenario called, to the scenario cargo transport. So cargo transport was problematic because of two things. So it's basically a two-dimensional problem. In cargo transport, we have a multiplicity of goods. So for example, we want to ship coffee, cars, spices, oil, and so on. And on the other hand, we have the multiplicity of storage and transportation methods. Trains, ships, planes, and so on. And in these scenarios, there are multiple challenges, and two main questions in these challenges are, how do these goods interact? Because maybe it's not the best idea to store coffee next to spices because they can interact with each other during transport. Or a more exploding example would be oil next to fireworks. You don't want to ship these two things together. And the second question is, of course, the main question, how can we quick and smooth do packaging and delivery? Because different goods require different means of transport and so on. And what really revolutionized cargo transport in 1950 was the invention of intermodal containers. So these are the things that you find on ships or on harbors, as you can see on the slide here. And when you take a more abstract look at the scenario, you come to the conclusion that two core principles are the main contributors of the success of intermodal containers. And the first one is isolation. So, for example, we can package all our coffee in one container, package all our spices in one container, and ship them with the same train. So the first principle is isolation. The second one is standardization. So these intermodal containers have equal size and equal shape. So by introducing this kind of standardization, tools form around it. So for example, there are forklifts which we see here in this picture, who specialize on working with containers, or also trains and ships and planes. So standardization and isolation are these two core principles which are responsible for the success of these containers. And as it turns out, we can map this scenario to modern software delivery. Yes, slide looks okay. So in software delivery, we have the same two-dimensional problem, right? We have a multiplicity of servers. For example, we have HTML frontends, we have algorithms in the business logic, analytics frameworks, or think about YouTube. YouTube must have an enormous storage engine to store all these videos. And in the other dimension is a development architectures that need to scale out on clusters, on big data appliances. And here we are talking about hundreds of nodes and thousands of cores where we need to scale out our solutions. And as well, cloud providers are also getting more popular. So here we have the same kind of challenge, right? And in literature, this challenge or this problem is often referred to as the DevOps barrier. DevOps short for development and operation. And you see this DevOps barrier here at this horizontal line. And in order to break this DevOps barrier, container-based virtualization is used. Or this technique helps us to break the DevOps barrier. So basically, the scenario is like this, right? So, and virtualization. And a lot of people come to me and say, well, Andy, you're a DevOps engineer. You know all about containers, and containers are just some virtual machines, right? And the first lesson that we learned today is containers are not virtual machines. So everyone has to remember that. So, containers are not virtual machines, but what are containers though? And this is best explained but by comparing them to virtual machines. So let's see how virtual machines work. So on the bottom we have just a piece of hardware, such as my notebook here, and on top of it we run an operating system. Then there is an isolation layer, which is called the hypervisor. And the hypervisor basically emulates or virtualizes a whole PC. So we have a virtual CPU, virtual RAM, virtual disk, and so on. And on top of this virtual PC, a whole software stack runs. For example, with an own guest OS with binaries and libraries, and then the app that we want to execute in these virtual machines. And this approach has benefits and drawbacks, where the first benefit is that virtual machines are great in isolation. So unless configured otherwise, a process running in a virtual machine cannot access any data or processes running in another virtual machine. A drawback here in this scenario, however, is that this guest operating system introduces an overhead, because a virtual machine usually runs in user space, and if the virtual machine needs to execute privileged instructions, these instructions are then emulated by the hypervisor into something that runs into user space. So there is a computation overhead by both running a whole operating system on top of an operating system and translating privileged instructions into user space. And as it turns out, this drawback does not occur when talking about containers. So you can spot it easily by comparing just these two diagrams. So containers do not involve any guest operating system. So containers work as follows. On top we have also hardware and operating system, and then we have a container runtime. And the big difference between a container runtime and a hypervisor is that a container runtime does not emulate anything. So there is no virtual PC involved and no translation of any instructions. So what the container runtime does is basically it creates an isolated workspace on the host kernel with a container are stored in an isolated workspace, and all the processes run also separated. And therefore, the container runtime exploits two kernel features of the Linux kernel. The limit how much you can see. And this is also, these are also the main factors why containers are quite popular today, because there is no computation overhead, so they deliver near native performance by just running the application natively on the host kernel. So this is the big difference. Containers run on the host kernel, whereas virtual machines require container-based virtualization. So the biggest one is Docker. And there are two competitors. The first one is the Open Container Initiative, which is, I guess, the most interesting one because it's rather new, but two big players in the industry contributed to the Open Container Initiative, and these two are Google and Red Hat. The Open Container Initiative is more or less in the beginning, but it's worth to look out for them. The second one that I want to mention is LXC, which is the first, or was the first implementation of container-based virtualization, dates back to 2011. But you know, it's like HD, DVD, and Blu-ray, so there can only be one, and this one is Docker. So Docker is the platform or the implementation that experiences adoption in industry. Okay, so in the remainder of this talk, we focus on Docker for the default implementation for container-based virtualization. So let's talk about the the Docker platform and do some terminology. So the container runtime in the Docker platform is the Docker daemon. So it's just a process on a Linux operating system which realizes the container runtime. Then we have to differentiate between a Docker container and a Docker image, because a Docker container is just a runtime instance of a Docker image. And a Docker image is more or less the basis of a Docker container, and it boils down to some execution parameters, for example, configuration for namespaces or C groups, and then a stack of file system changes. And this is one of the beauties of the Docker infrastructure, because in Docker, the file system is structured in the form of layers, which you can see, hopefully, here in this diagram. So for example, if we take a look here in this diagram at the app C and app CTIC, these two apps, let's say, share different layers of file systems. So in one Docker image, the file system is structured in layers, and if we do any modifications in the file system, this modification causes another layer on top. So for example, here we have on the top layer, let's say the libraries and binaries of the Debian distribution. We have the Java runtime on top of it, and then the Tomcat applications. So it's like a stack done with Legos, where we can just put one piece after another. And if there are any file system changes, this change is then persisted in the form of a new layer on top of it. Okay, the last term, I guess, that we have to mention is a Docker file, because Docker files make the whole ecosystem efficient. Because Docker file is the technique how we can create new Docker images. And it's literally a text file which contains the commands that you usually execute in order to build a Docker image. So we see an example, I guess, in 2 or 3 minutes when we start a demo. Yeah, demo time today. Short break. Okay, demo time. Everyone can see my shell, right? Perfect. In the back there, just my colleagues, they don't eat about this. Okay, what I want to show you in the demo is a whole journey from existing source code. We want to containerize an application that I wrote on the weekend. create an image out of it, then launch a container and run this image in the form of a container, and then, let's say, simulate how we can transport this Docker image to customers then. Okay, so I did a lot of coding and I came up with a really sophisticated Hello World app in Python. So please raise your hand if you know Python code. Fair enough, perfect. So basically what you see here is just a web application realized with Flask, running on any interface on my laptop on port 5000, and I just return hello League of Geeks audience in an index route here. This whole app depends on one dependency, which is flag, which is a Python library that brings the web server here. So, and as this is a Python script, we specify our libraries and dependencies in a file called requirements.txt, and that's exactly what happens here. So we have the Flask, and we need Flask in version 1.1.1. So now let's turn this awesome complex application into a Docker image. And therefore, I have prepared a Docker file. And this Docker file, to transform this small Python application into a Docker image, looks like this. So it has basically 6 instructions, here, here 2, and this is the last one. And a Docker file is more or less a script that is executed by the Docker daemon, which creates the Docker daemon out of this script. And the first instruction here is a from statement. This from statement realizes inheritance or reuse. And in this example, we state that we want to inherit all the binaries and libraries from the Debian 9 Slim image. So the Debian 9 Slim image is or contains libraries and binaries of a slimmed down variant of the Debian operating system. And we take this as a start point because we basically never create Docker images from scratch. So we always choose a starting point using this, this from statement here. And then we have a copy statement. A copy statement just copies files or directories from the host file system to the resulting Docker image. This happens in instruction 2 and 3. And now things get interesting, because here we have a run statement. A run statement, people who are familiar with the Linux shell, please raise your hands if you are familiar with the Linux shell. Awesome, so I don't have to explain anything. So this updates repositories and installs the Python interpreter here, right? So, and what happens under the hood when building this Docker file is that the Docker daemon will spawn an intermediate container and will execute these commands inside this container, and then detects changes in the file system. And if there are any file system changes, a new layer is added on top of the layers that we have before. So the layers of the Debian system and also the layers that are created here. So this happens in this line and also in this line, where we just install our requirements from the requirements.txt, and we end up in the last line here, which is a command statement. And a command statement does not add any file system layers on top of the Docker image, but it acts more like an entry point, which is the command that is executed when the Docker daemon launches a Docker container from the Docker image. So, got it right. Now, let's just build this, this Docker file with Docker build, and I can give it a name with the T flag here, and I name it Geeks example. And as it turns out, well, I prepared this is cached. Usually it takes a little longer, but anyhow, we have a successful build message here. So this is how we get this existing code into a Docker image. So now if we, let's say, simulate the realistic scenario, we have our application in the right, with the right dependencies, and everything fits together. And now we want to transport this Docker image to the customers. And therefore, we can use a command that's called docker save. And docker save, when I enter the name, I can export Docker images to tarballs. And I just pipe it in an image.tar. Oh, it's Geeks example. And then I have something that I can ship to customers, which is really great. The inverse process of loading such an image is done with docker load. And then on the other side, when I'm at the server of my customer, I can load this image into the Docker daemon, and then I can spawn containers out of it. And spawning containers is just done with docker run. And I can start it up perfectly. Okay. So this is basically like it's a very basic example, but it covers most of the steps that you do in practice. So what happens in practice is we have source code that's delivered by developers. We pack it in a Docker image. We ship this Docker image, and then we, on the customer side, we load it and can execute this image quite properly. Okay. So to wrap this section up, the next two questions are, well, why do developers get, or why should, if anyone wants to adopt this technology, why should developers care, and why should developers think about this technology? Developers should care, why? Because they build once and they run anywhere. So they get a clean, safe, portable runtime environment for their app, and there's no more dependency hell or mismatching versions. So I have a lot of experience in carrying out solutions to customers, and I mean, a successful installation on the first time is possible, but not very probable, because you depend more or less on the operations guy on the other side, and you basically always end up in a dependency hell or have to deal with mismatching versions of your dependencies. And with Docker Container, you eliminate this drawback. You can improve and automate testing, integration, and packaging, which is also a very strong argument, because at OneLogic, we improved integration testing, for example, because now we execute our integration tests, and these tests they query against whole stacks of infrastructures, because we can just start the Docker containers and run our tests against these containers, and they more like simulate a way how to get a production near environment. You eliminate compatibility issues on different platforms. So basically, you can run these Docker containers everywhere Docker daemon is. You can even run it on Windows. By the way, I don't recommend it. So Docker on Windows is broken. Docker on Mac is okay. But if you want to try out the technology, just use Linux. And we reduce any other pain points during subsequent deployments. On the other hand, so if we just switch camps, from the operations or administrative perspective, our credo here is we configure once and we run anything. So we can make the whole life cycle more homogeneous, portable, and reliable. We eliminate inconsistencies between different kinds of environments because we just boil down to Docker containers and the Docker daemon. And the third one is also important. It supports segregation of duties. Because if you work in an environment and you have different teams, you always have the question, who is responsible for that? The introduction of Docker in our company showed us that it draws a very clean interface what a developer has to deliver, which is a Docker image, and an operations guy has to consume, which is also a Docker image. And it supports this segregation of duties. It improves continuous integration and deployment systems, and of course is cost efficient. And I have an example for cost efficiency when we talk about use cases, which is the second part. So cheers. So now I want to present 2 use cases that we established at my company, OneLogic. And I want to present you the lessons that we learned from that in kind of an experience report. And the first use case is around containerizing our product, which is called OneData. So what you need to know about OneData is that it's a software with a web front end, and it's composed of different components. So the OneData software stack uses, or it's in the transition of moving towards a microservice architecture. So there are several backends involved, all based on Spring Boot. We have different front ends in AngularJS and Vue.js. We have different script environments for Python and R scripts. We store data in databases. And for the analytics algorithms, we use a Spark cluster with HDFS as backend. And at OneLogic, we have different developer teams. So we have 3 teams that purely do developing. We have one DevOps team, we have a UX and UI team, and we have a quality assurance team, right? And each of these teams require one instance of the OneData software stack to develop or test against. And before, we operated an instance of the OneData stack by using a virtual machine-based approach. So basically, we opted in for AWS, and we chose the EC2 T2X large instance to run a developer instance. It has just 4 CPUs, 16 gigs of RAM, 200 megabytes of storage, but is around 160 euros per month. And as we grew, or as we gathered the know-how in container-based virtualization, we started to containerize the whole OneData software stack. And by leveraging the isolation and standardization principles of container-based virtualization, we were able to run multiple stacks of our OneData software next to each other on the same host. So we were able to create 6 instances of the OneData software stack on a dedicated server that we purchased from Hetzner, great company by the way, and this has way more powerful specs. We have an i9 here, 46 gigs of RAM, a little bit of non-volatile memory, and it's way cheaper. And instead of purchasing 6 EC2 instances, we ended up with just one dedicated server at Hetzner's, and we could reduce the operations cost this way by a factor of 12.86. And this is quite significant. So if you tell management that you can reduce the cost by a factor of 12, you know that's a win for everybody. And this is basically the first use case. Here we can leverage the resources of our dedicated machine way more better than compared to virtual machines. The second use case is a little more complex because it's concerned around the software delivery process at our company OneLogic, and this is the status 2 years ago. So what happens in this scenario is as follows. I start to explain these scenarios by introducing the first 2 entities. The first entity is the customer. So the customer wants to use our software, which is OneData, analyze his data and get some value out of it. The customer talks with a customer success manager, which is a guy at OneLogic, which does all the talking. So the customer says, well, please install a new instance of OneData at my machine, or update it, or do a little change. And what the customer success manager does is he calls basically me, he calls DevOps and says, yeah, well, we have this customer and he wants to update to a new version of OneData, right? So, So I talk with developers, and developers do what developers do. They implement source code and push it into Git repositories. This code is then built by a continuous integration system, and we as DevOps, we get the software artifacts out of this continuous integration system, and now the pain begins. Because, this is a little special related to OneLogic because we do data analytics and data science. So we analyze data of the customer, and this data is very sensitive to the customer because it's like cash flow or internal processes and so on. So the customer does not want to transfer his data somewhere else as in its own infrastructure. So this server, where the software artifacts have to run, are in a highly secured environment. And it's only accessible by a highly secured VPN connection. So, and what literally happens is the following. So in order to transfer the software artifacts, I create tarballs of the software and store it on a thumb drive. This is necessary because I have to load the software on a special customer laptop. So these VPN connections are so secure that they only are accessible by whitelisted hardware. So the customer provides us with an own laptop which can access then the VPN. So I run around the company and search for the customer laptop. Then I have the customer laptop and run again because I need to fetch a security token which I need for the two-factor authentication for the VPN. So finally, I can establish the VPN connection and transfer the artifacts to the server. But then the story is unfortunately not over because, as I said before, then you are dependent on the operations guy that all your software dependencies are, on the one hand, installed and are there in the right version. And unfortunately, experience tells us that this is not always the thing. So if you find that your infrastructure is not in best shape, the whole loop begins again. And this is purely pain. So in order to ease the pain, we introduced container-based virtualization here. So we pimped our continuous integration system and added Docker files, which automatically build Docker images instead of Python scripts, WAR files, and so on. You know it. And we store these Docker images in a Docker registry. And now we just ship Docker images instead of the plain software artifacts. And on the other hand, we don't need much from the operations guy here because the only requirement that we have is please provide us with a Docker daemon and everything is fine. And we love this solution. Also, the customer loves this solution because the customer needs to install just one software dependency and everyone is happy, right? So this is a big win for everybody. This is a win for the customer and this is also a win for the development team. But anyhow, there's still one problem left, and this problem is the DevOps barrier that you see here, right? So there's a huge DevOps barrier by going through this whole tunnel here with the VPN and the customer's laptop. So what we did in order to tackle this problem is introducing a concept that's often referred to as GitOps. This method flies around some Kubernetes literature, but it can also be adopted if you just use some plain containers with Docker. And the method works like this. So as a central component of the GitOps process is a Git repository that is accessible from both the operations side as well as the development side. And in this Git repository, we store the configuration that is used at the customer server to spawn the containers that run our application. And also in the middle here, we have a Docker registry, also accessible from both sides. So what happens when the customer calls the customer success manager? The customer success manager interacts with the continuous integration system that we pimped in order to include continuous delivery capabilities. So what happens exactly is that the customer success manager specifies the change in a graphical user interface in our Jenkins, that's Jenkins logo, and in a Jenkins pipeline, also in a pipeline of the continuous integration system, we do a change in the configuration files and push it to the version control system that holds the configuration. On the other side, we have a GitOps container here, and the GitOps container just pulls regularly from the Git repository if there are any configuration changes. So for example, there was a bump in the version number or just some property that is activated or anything else. And if this GitOps container detects a change, it pulls all the binaries from the Docker registry and auto-configures itself on the server. And this way, there is a full automation from the customer success manager that specifies the change in the continuous delivery system to the operations side where the secured server of our customers run. And as it turns out, we could convince several customers who run in this setup where this server here has very limited access to give us access to the Git repository and the Docker registry, which has basically two factors because both protocols use HTTPS. So they just needed to, let's say, whitelist our server IP on the HTTPS port, and all traffic is here encrypted. So we basically convinced every customer to whitelist our services and establish here a full automation of our software delivery process. And now finally, so this is very fresh. It's operational like 2 or 3 weeks. So it turns out really great, and it eases the pain a lot. So to conclude this, what are the lessons that we learned? So by establishing container-based virtualization at OneLogic, we are now able to deploy and scale out solutions on cloud platform providers, on very hard server targets. We can push our solutions to AWS, Azure, GCS, and so on. We have a new building and packaging mechanism, which is very homogeneous. And we improved stability and reliability, and as well introduced a standardized backup and restore procedure, which was kind of a side product of this whole standardization. Because if you have different kinds of servers, different operating systems, the backup mechanism changes in a way. But as we roll out containers now, we have a standardized way of executing and operating our system. So we have now a standardized backup and restore procedure. We improved our continuous integration by enabling end-to-end tests using near-prod near infrastructure, and we draw a lot of benefits out of the GitOps process. So we have fully automated continuous delivery pipeline, supporting, let's say, semi-air-gapped servers, which are servers that cannot reach something out of the internet and are just accessible via VPN connections. We increased the customer's trust by a lot because it really happens that the customer calls the customer success manager, and the customer success manager can roll out this update within hours, which is really, really fast because fewer people are involved in the process and it's fully automated. And we could hand over all the know-how that we establish at DevOps to other departments in the company, for example, customer success management, which can do a lot more than before, and reduce the operation costs by a lot. So this is important for management, but Okay, Sarah, how am I in the time? I forgot to start my timer. To be honest. Okay. So I guess I fly over the last few slides. So what happens next is if you get container-based virtualization into practice and master this technique, the next step is container orchestration. Container orchestration is nowadays done with a technique called Kubernetes, and this is a citation from the website. So Kubernetes is a portable, extensible open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. In other words, do I have other words here? yeah, so this is the architecture of Kubernetes. We skip this because it's complicated and yeah, you know. I just tell you what Kubernetes does and what Kubernetes does not. So Kubernetes is more like a platform which provides an environment for your Docker containers on a cluster. So if you have a lot of Docker containers and a lot of services that you want to operate, and all these containers do not fit on a single machine, you can run it on the Kubernetes cluster. Where Kubernetes is really strong is abstraction. So it introduces a lot of abstract concepts. Well, what is an app exactly? What is a service, deployment, ingress, and so on. And there are several layers of abstraction which makes the Kubernetes platform very performant. It provides a means to scale out your application because you can just throw containers at your Kubernetes cluster and they distribute by themselves. And you have a means to perform like some technologies like automated rollouts, rollbacks, green, blue deployments, and so on. But what Kubernetes does not do is it provides any additional application level services. So it's just Docker, but Docker on a cluster in more abstract way. Kubernetes does not auto-scale your application. So the scaling mechanisms need to be implemented and need to be well defined. And it does not compile or build your source code in any way. So Kubernetes makes things run more smoothly, but it's more complicated, let's say it this way. So let's come to the conclusion of the talk. So what we have seen is that container-based virtualization is widely established worldwide in IT companies. We have learned that containers are not virtual machines. Takeaway message number 1 today. We have seen a lot about Docker. We have seen a basic demo where we can build Docker images out of existing source code, package them in tarballs, and transfer them to customers and unload them. We have seen 2 use cases. The first one is a use case around containerizing your application and leveraging the resources of your server and reducing operation costs. The second use case is around the delivery process, which facilitated delivery at OneLogic and now really saves time. And the last slide we skipped because this was the Kubernetes architecture. So thank you very much for your attention. I'm happy if you have any questions, I can answer them.